This is video 4 in the lecture on cell balancing. In this video, we'll discuss when to balance, both the low-level firmware consideration of interweaving balancing with measurement and the algorithmic question of at which state of charge it is best to balance. The relative timing of balancing and measurement is an important firmware detail. We'll discuss it in the context of this circuit. In brown, we see the measurement pathway, the filter resistors and filter capacitors that constitute an RC filtering network, and the analog to digital converters that measure each cell's voltage. In black, we see the cells on the left and the components involved in balancing on the right. We have the balancing resistors on the PCB and the balancing MOSFET switches on the BMS chip. In purple, we have the wire harness, consisting of connectors and the wires themselves. The parasitic resistance of these components is shown explicitly. BMS ASICs are carefully designed for tiny input currents during measurement to result in tiny voltage measurement error. Even a small balancing current is likely orders of magnitude larger than the measurement input current. Say we design for a 20 milliamp balance current. 20 milliamps across a parasitic 1 ohm of the cell sense wire gives a 20 millivolt drop on each wire, for a total measurement error of 40 millivolts on that cell. That is a significant error, too much to accept in many applications. Another option, BMS ASICs are carefully designed for tiny input currents during measurement to result in tiny voltage measurement error. Even a small balancing current is likely orders of magnitude larger than the measurement input current. Say we design for a 20 milliamp balance current. 20 milliamps across the parasitic 1 ohm of the cell sense wire gives a 20 millivolt drop on each wire, for a total measurement error of 40 millivolts on that cell. That is a significant error, too much to accept in many applications. One solution is a duplicate harness with 2 wires to each cell, one for balancing and the second for sensing. Cost and mechanical complexity are often prohibitive for the dual harness solution. Another solution is to interleave balancing and precision cell voltage measurements. During balancing, the system takes coarse cell voltage measurements, sufficient for safety monitoring. On what timescale do we do this interleaving? One possibility is to do it on a timescale of hours. If the application has a daily cycle, as you might expect with solar energy storage or a family car, we might find time periods when the system is charging or discharging and we want precision measurements, and another regular time period when the state of charge is constant and balancing is convenient. Let's work through an example of what this means for a design. Let's target correcting for a 17 milliamp imbalance. That was our worst case estimate. Assume that the application spends 8 hours charging, 8 hours discharging, and 8 hours resting. That gives us 8 hours to correct for the imbalance accrued in every 24-hour time period. We can rearrange terms and solve. We need an average 51 milliamp balancing current. Since many designs cannot balance adjacent channels, we will alternately balance odds or evens. In other words, the instantaneous current is doubled, since any given channel is balancing only half the time. We can calculate the heat dissipated in each balancing resistor. 0.43 watts is a bit much for a single component, so we'll need to implement each balance resistor as several series resistors. The PCB will dissipate 2.6 watts, which is high enough that some thermomechanical design is probably needed. The heat dissipation inside the chip is low enough that a chip with an exposed pad will see a relatively small temperature rise relative to the PCB. You could at this point do the analysis to see whether a chip without an exposed pad might suffice. Some applications don't have a regular rest period, or we wish to design for a lower balancing current. In those cases, we can interleave precision voltage measurements and balancing on a smaller time scale. We can monitor with high precision for 100 milliseconds or 1 second or some similar length of time, and then balance for a few hundred milliseconds or a few seconds with the consequently higher measurement error. For the precision measurement window, we should choose a duration longer than the time constant of the BMS chip's internal low-pass filter. It's also convenient to make this duration some multiple of the frequency at which the microcontroller communicates with the BMS chip. Typically, this approach enables balancing for a larger fraction of the time than the previous approach. And in turn, that enables a lower instantaneous balance current. By balancing more of the time, we can get away with a correspondingly smaller balance current. Another idea is firmware compensation. The firmware can take the voltage measured during balancing and subtract from it a value that approximates the expected voltage drop due to the balancing current. The compensation voltage Vcomp in this equation would equal the nominal balancing current times the nominal parasitic resistance between the chip and cell. The residual error will be a function of the variation in wire harness impedances and the magnitude of balancing currents. You can and should characterize this variation for a specific design, but I might guess that balance currents may vary by 30% due to temperature and component variation and aging, and parasitic resistances may vary by 50% or even more. The resulting residual error may be fine for some SOC estimation purposes, and yet, in many cases, may be too much for assessing pack imbalance. Firmware compensation is a good idea to consider and relatively low cost to implement. Let's ask one more question around balancing. At what state of charge is it best to assess imbalance? Or at what point in the operating profile? My car might drive to run errands around town, then charge at night and rest for a few hours in the early morning. The next day, maybe we go on a day hike and drive up into the mountains, then come back and charge at night, again with a rest in the early morning. The system has a very convenient opportunity to take a high precision measurement most mornings when the battery pack is well rested and when very little current is flowing. Based on that, the system can make a fairly accurate assessment of pack imbalance and create a feed-forward plan for how much balancing needs to be done over the next 24 hours to correct the existing imbalance. Since the slope of the voltage versus SOC curve is moderately steep for the NCA cells or NMC cells in my car, where on the curve we take the measurement is not very consequential. Recall that a given measurement error, say 5 millivolts, will have a larger impact on the SOC estimate when the slope is flat than when the slope is steep. An energy storage battery used for grid stability, on the other hand, is intentionally operated around 50%. Oftentimes, LFP cells make most sense for stationary storage, where their advantages of better safety and better cycle life outweigh the disadvantage of slightly lower energy density. A battery can operate for many cycles in that very shallow middle part of the curve, where estimating SOC from voltage is very difficult. In this scenario, the pack can become unbalanced, and the voltage difference may be too small to detect in the application. A possible solution to keeping an LFP energy storage system pack balanced is to occasionally cycle it deeply and assess imbalance where the voltage SOC curve is steepest. Oftentimes, grid energy storage involves multiple battery packs. In principle, one of the multiple packs can be selected from time to time for deeper cycling. The trick is coordination. Balancing is usually thought of as something that a pack does internally and implemented thus. The idea on this slide requires a central controller to coordinate the packs and requires each pack to communicate its imbalance externally. Let's summarize the key points in this section. Balancing current causes a voltage drop along the connection to the cells, causing measurement error equal to the product of the balancing current and the parasitic resistance between cell and sensor. Mitigations include a dual harness with separate sense and balance wires, though in practice, cost and mechanical complexity are significant hurdles. Interleaving precision measurement and balancing allows for precise measurements when balancing current is not flowing. This can be implemented with the interleaving on a timescale of hours, or fractions of a second, or both. Firmware compensation can reduce the residual error, and this is inexpensive to implement, but may not be sufficient on its own. Balancing and assessing imbalance don't have to happen concurrently. Assessment of the imbalance is best done when the pack is rested and at a steep part of the OCV-SOC slope, which is challenging for LFP packs operated mid-range, such as for many stationary energy storage packs. This completes the lecture on cell balancing in my Battery Management Systems course. If you liked what you saw, please help this course get seen. Share it with a colleague, share it with a customer, share it with a favorite college professor, and of course, subscribe, comment, and like.